The light was ancient, older than the Earth, older than the Sun, older than almost every structure humanity has ever seen. A tiny signal traveled across an expanding universe for more than 13 billion years before finally reaching a machine floating above our planet. And when scientists decoded what it contained, something felt wrong. The galaxy should not have existed, not that early, not that massive, not that organized. According to everything researchers thought they understood about the young universe, there was not enough time for something like this to appear. But there it was, hidden in the darkness. A structure from the beginning of time that forced astronomers to ask a dangerous question. Did we misunderstand how quickly the universe could build itself? This is the real story of James Webb's most surprising distant galaxy discoveries. On December 25th, 2021, humanity launched one of its most ambitious scientific instruments ever created. The James Webb Space Telescope lifted away from French Guiana aboard an Ariane 5 rocket. Built through a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, Webb was designed to do something previous telescopes could not: look backward. Not through time travel, but through light. Because when astronomers observe distant objects, they are not seeing them as they are today. They are seeing them as they were when that light began its journey. A star, 100 light years away, is seen 100 years in the past. A galaxy billions of light years away is a message from an ancient universe, and James Webb was built to read the oldest messages ever written. Its mission was extraordinary. A telescope almost 6.5 meters wide, a sun shield larger than a tennis court, a position nearly 1.5 million kilometers from Earth at the second Lagrange point, a location where it could remain cold enough to detect the faint infrared glow of the earliest cosmic objects. Because the first galaxies were not shining invisible light anymore, the universe had stretched their light, redshifting it into wavelengths invisible to human eyes. Webb was created specifically to capture those hidden signals, and scientists expected discoveries. They expected surprises, but they did not expect the universe to appear ahead of schedule. The first major shock arrived soon after Webb began releasing data. In 2022 and 2023, researchers studying some of Webb's earliest observations started identifying galaxy candidates at extreme distances. These objects appeared to exist only a few hundred million years after the Big Bang, a period when the universe was supposed to still be chaotic, dark, and only beginning to form its first structures. At that stage, scientists expected small groups of stars, early building blocks, the cosmic equivalent of construction materials scattered across an unfinished universe. Instead, Webb appeared to be finding something else: galaxies that looked mature, complex, and surprisingly bright. One of the most discussed discoveries came from observations of galaxies with redshifts, indicating they existed less than 400 million years after the beginning of the universe. That number is almost impossible to imagine. 400 million years sounds enormous from a human perspective, but cosmically it is almost nothing. Earth itself is about 4.5 billion years old. The universe is about 13.8 billion years old, meaning these galaxies appeared when the universe was only a tiny fraction of its current age. And yet some looked like they had already gone through millions of years of development. That created the first major mystery. How could the universe build something so complicated so quickly? Scientists did not immediately abandon existing theories. Science does not work that way. A strange observation is not automatically a revolution. First, researchers check the instruments, then they check the calculations, then they check whether another explanation fits the evidence better. And James Webb had already demonstrated something important. The universe was much more active in its early history than previously observed. But the question remained: was Webb revealing a genuine problem with cosmology? Or was it revealing that the universe was simply more complicated than scientists expected? To understand why these discoveries mattered, you need to understand the original timeline of cosmic evolution. After the Big Bang, the universe entered a period called the Cosmic Dark Ages. There were no stars, no galaxies, only a hot mixture of particles expanding and cooling. Eventually, gravity began pulling matter together. Small differences in density became larger. Gas collapsed. The first stars ignited. Those stars created heavier elements. Those elements helped form later generations of stars and galaxies. According to traditional models, this process required time, a lot of time, but Webb was finding possible evidence that nature had moved faster, much faster. Anomaly. 1. The brightness problem. Some early galaxies detected by Webb appeared far brighter than expected. Brightness tells scientists several things. It can reveal how many stars exist, how much gas is being converted into stars, and how efficiently a galaxy is producing light. A galaxy appearing this bright so early suggested either the universe formed stars extremely efficiently, or scientists underestimated how quickly massive galaxies could develop. Both possibilities were significant. Anomaly 2. The maturity problem. Some galaxies did not simply appear bright, they appeared structured. They showed signs that stars had already gone through generations of evolution. But creating heavier elements requires earlier stars to live and die. The universe needed time to manufacture these ingredients. Finding evidence of complexity so early was like discovering a fully developed city in a region where only a few temporary buildings were expected. The question was not whether the city existed. The question was, how was it built so quickly? By early 2024, astronomers around the world were analyzing thousands of Webb observations. Every new dataset added more pieces to the puzzle. Some researchers argued that the findings could represent a major challenge to existing models of galaxy formation. Others argued that the discoveries were being misunderstood, because distance in astronomy is incredibly difficult to measure. A tiny error in interpretation can transform a young galaxy into an older-looking one. A false assumption about brightness can create an illusion of mass. A measurement mistake can become a scientific headline. So researchers returned to the data. Again and again. One scientist who became closely associated with discussions around Webb's early galaxies was astrophysicist Peter von Dockum. Researchers studying early galaxies began debating whether these observations represented missing pieces in current theories or signs that the universe itself had different rules during its earliest moments. The possibilities were enormous. If galaxy formation happened faster than expected, scientists might need to refine their models. If something fundamental was wrong, the consequences could reach into our understanding of dark matter, cosmic evolution, and the origin of structure itself. But there was another possibility, a much simpler one. Maybe these galaxies were not breaking the rules. Maybe scientists were finally seeing the universe clearly for the first time. James Webb was not just a more powerful version of older telescopes, it was looking into a completely different part of reality. And every new instrument in astronomy has done something similar. It has revealed that the universe is more complicated than previous generations imagined. The telescope does not change the universe. It changes what humanity is capable of seeing. The universe was not supposed to look like this. That was the feeling spreading through astronomy communities as more James Webb data arrived. Not because scientists had discovered something impossible, but because they had discovered something unexpected, and unexpected discoveries are where science changes. When researchers examine ancient galaxies, they are not simply looking for distant points of light. They are trying to reconstruct the childhood of the universe itself. Every galaxy is a clue. Every star is evidence. Every chemical element tells a story about what happened billions of years ago. And Webb had opened a window into a period humanity had never directly observed before, the first few 100 million years after the Big Bang, a time when the universe was still becoming recognizable. Then, in early 2023, researchers announced some of the first major results from Webb's deep field observations. Among the objects detected were galaxy candidates with extreme redshift values. One of the most famous examples was a galaxy candidate known as JADES-GS-Z 13-0. It appeared to exist roughly 320 million years after the Big Bang. A cosmic newborn, almost at the beginning of everything. Yet its light suggested that it was already producing enormous amounts of energy, already forming stars, already becoming something larger than expected. The discovery immediately raised a question. Not, can galaxies exist this early? Scientists knew they could. The question was, how large and developed could they realistically become in such a short amount of time? Because galaxies do not appear instantly. They require gravity, gas, dark matter, stars, supernova explosions, chemical enrichment, a complicated chain of events stretching across cosmic history, and Webb seemed to be finding some of the final chapters inside what should have been the opening pages. But before rewriting textbooks, scientists needed confirmation, because measuring the distance of an ancient galaxy is extremely difficult. The process depends on studying how much the universe has stretched the object's light. This is called redshift. As space expands, wavelengths of light become longer. The farther the light travels, the more it stretches. The more it stretches, the farther back in time scientists can look. But early galaxies are incredibly faint. A tiny signal buried in noise can create uncertainty. So astronomers began collecting more data. The first step was spectroscopy. Instead of simply taking an image, scientists separate the light into its individual wavelengths, like a cosmic fingerprint. Spectroscopy reveals chemical signatures. It confirms distance. It tells researchers whether they are truly seeing one of the earliest galaxies ever observed. And when Webb's instruments confirmed some of these extreme distances, the mystery became stronger. The galaxies were real. The question remained, how did they become so advanced? By mid-2023, astronomers were exploring several possible explanations. None required abandoning modern physics, but each possibility changed how scientists understood the early universe. Possibility 1. Star formation was more efficient than expected. Maybe the first galaxies were incredibly productive. A young galaxy contains massive clouds of hydrogen gas. Under the right conditions, gravity compresses that gas until stars ignite. If early galaxies converted gas into stars faster than current models predicted, they could become brighter much earlier. The universe may not have been slow, it may have simply been extremely efficient. Possibility 2. The galaxies were powered by black holes. This possibility was even more fascinating. A galaxy does not only contain stars. At its center, many galaxies contain supermassive black holes. When these black holes consume matter, they can release enormous amounts of radiation. These active regions are called quasars, or active galactic nuclei. A young galaxy appearing unusually bright might not be entirely powered by stars. It could be hiding a rapidly growing black hole. And that created another mystery, because black holes themselves have a growth problem. The earliest known supermassive black holes are enormous, millions or billions of times more massive than the Sun. But how did they become so large so quickly? A question about galaxies became a question about the origins of black holes, and suddenly Webb was not just studying the first galaxies, it was investigating the first giants of the universe. Possibility 3. Our models were missing something. This was the idea that attracted the most attention. Maybe the equations used to predict early galaxy formation were incomplete. Not wrong, but incomplete. Scientific models are not perfect descriptions of reality. They are tools. They improve as new evidence appears. Newton explained gravity. Einstein expanded our understanding. Quantum physics changed the way scientists viewed the smallest scales of nature. Astronomy has always progressed when observations forced humanity to refine its ideas. However, some headlines suggested Webb had broken cosmology. That was an exaggeration. Scientists were not throwing away the Big Bang theory. They were not claiming the universe was wrong. The Big Bang remains supported by overwhelming evidence: the expansion of space, the cosmic microwave background, the distribution of galaxies, the abundance of hydrogen and helium. These discoveries did not destroy cosmology. They tested its details, and testing is how science moves forward. Meanwhile, researchers continued examining another possibility. Maybe some of Webb's earliest galaxy candidates were not as massive as they first appeared. Dust can affect observations. Young stars can create unusual brightness patterns. Different assumptions about galaxy structure can produce different conclusions. The universe is complicated, and the first observations of any new telescope often reveal surprises that require careful interpretation. But then came another unexpected discovery. The mystery was not limited to distant galaxies. Webb began finding evidence that the early universe contained objects with structures scientists never expected. Some looked strangely mature. Some contained organized shapes. Some appeared to have already experienced major episodes of star formation. The universe's childhood was not looking simple. It was looking crowded. In September 2023, researchers studying Webb data identified another ancient galaxy candidate called CEERS-93316. At first, it appeared to be among the most distant galaxies ever detected. Later analysis suggested its distance estimate was lower than originally thought, and this became an important lesson. Webb was not just discovering new galaxies. It was also teaching scientists how carefully they needed to interpret the new universe being revealed. Every discovery had to survive intense examination. This is the process that separates astronomy from speculation. A strange signal appears. Scientists investigate. Other researchers challenge it. New observations arrive. The explanation becomes stronger. Or it disappears. The universe does not change to match expectations. Expectations change to match the universe. But one fact remained undeniable. James Webb was seeing farther back than any telescope before it, and it was finding a universe that was more active, more complex, and more surprising than anyone predicted. The first galaxies were not simple clouds slowly gathering themselves together. They were dynamic environments, places where stars were being born, black holes were growing, matter was organizing itself. The cosmic dawn was not a quiet sunrise, it was an explosion of creation. And then researchers noticed something even stranger. Some of these ancient galaxies appeared to contain signs of elements that should have required multiple generations of stars to create. Carbon, oxygen, other heavier elements. The ingredients needed for more complex cosmic structures. But where did those ingredients come from so early? Who created them? And how quickly did the universe manufacture the building blocks of everything we know? Because hidden inside Webb's discoveries was a much deeper mystery. The question was no longer only, how did the first galaxies form? It became, how quickly can the universe transform simple matter into complexity? The universe has a memory, not a memory made of words, not a memory stored in machines, a memory written into light. Every photon traveling through space carries information about where it came from. When James Webb captures that ancient light, it is reading a message that began before Earth existed, before the sun was born, before the Milky Way looked anything like it does today. And hidden inside those messages was another surprise. The first galaxies were not just forming stars, they were already changing the chemistry of the universe. To understand why this mattered, scientists had to look at the ingredients of creation. After the Big Bang, the universe was almost entirely made of hydrogen and helium, the simplest elements. There was almost no carbon, no oxygen, no iron, no silicon. The materials needed to create planets, oceans, and eventually life did not exist yet. Those elements were created inside stars. Stars became cosmic factories. They burned hydrogen into heavier elements. When massive stars died, they exploded as supernovae, spreading those elements into space. Then new stars formed from that enriched material, a cycle of cosmic recycling. But this process takes time. A first generation of stars must be born. They must live. They must die. Their remains must mix with surrounding gas. Then another generation must form. Scientists call these early stars population 3 stars. They are among the most important missing pieces in astronomy. The first lights after darkness, the first objects that transformed the universe. And James Webb was built partly to search for them. The telescope has not yet provided a confirmed direct image of a population 3 star. But its observations of ancient galaxies are helping scientists understand the environment where these stars may have existed, and the results suggest something surprising. The early universe may have been a much more active chemical laboratory than previously believed. This created another layer of mystery. If galaxies existed earlier than expected, and if stars were producing heavy elements earlier than expected, then something must have accelerated the entire process. Something was helping the universe build complexity at incredible speed. One possible answer leads to the invisible side of the cosmos: dark matter. Scientists believe ordinary matter, the atoms that make stars, planets, and humans, represents only a small fraction of the universe. Most of the universe appears to be made of something we cannot directly see. Dark matter. It does not emit light, it does not reflect light, but its gravitational influence is visible. It acts like an invisible framework, a cosmic skeleton. Galaxies appear to form around concentrations of dark matter called halos. These halos attract gas. The gas collapses, stars are born, galaxies grow. But what if those early dark matter structures formed differently than scientists expected? What if the cosmic skeleton was stronger, more efficient, more capable of pulling matter together? Then the first galaxies may not have needed as much time as older models suggested. The universe may have had a hidden advantage from the beginning. Another possibility involves the nature of the first stars themselves. Early stars may have been enormous, far larger than typical stars today. They could have burned through fuel quickly. They could have exploded violently. They could have created heavy elements at a remarkable pace. The early universe may have been filled with cosmic giants that lived short but powerful lives.